All right, so good morning, everyone. Today we're going to be going over the EC-6 science review, and some of the content will be useful for those of you that are taking the 4 through 8 science test. Okay, so some of that content will be overlapping. So today, our goal for the morning is just to get through competencies 1 through 10. And then there is that note taker guide, as I mentioned, that is in the chat. So you can, feel free to use that or just take notes on your paper. That's up to you. So in looking at the science exam, just like with all the exams, remember that you do want to be looking at your competencies. And just like in the social studies review, if you went to that one, my husband kind of went through that and showed you how we want to be paying attention to those verbs, looking at those nouns, right? And to dissect what it is that you have to know. Because again, when we look at the content, I know for the science, when I looked at it the first time, I looked at it through the lens of a high school teacher, right? But when you really look at the content and the competencies and the descriptors, it's not that complicated. So there's not really a lot of math that you'll have to be doing. It's more knowing the concepts and like the general formula. Okay, so just as a note for that one. So for the competency 1, this is basically just related to lab safety, materials, equipment. So, just I guess kind of common sense things, right? And you just want to make sure you have a safe environment for your students. There should be proper equipment that should be worn. So even if you're using something simple like vinegar and baking soda, you still want to make sure that your students have their eyes protected, right? So they should have some sort of goggles on, and they should have some sort of covering for their clothing. So in the elementary school, the types of chemicals that will typically be used are like household materials, right? So vinegar, baking soda, I don't know, like bleach or something, food coloring, stuff like that. But even with that, we still always want to make sure students are safe. That's going to build those good practices for them. So as they move on into the higher grades, they already know like what the expectation is. And you want to make sure that areas are always kept clean. We don't want clutter or anything, because again, that can be a hazard as they get older and they start working with like, Bunsen burners and hot plates and stuff like that. So with the science classroom, there is typically going to be a safety contract that will be sent out to parents. So students will have to sign it, parents will have to sign it. And it's basically just going over the rules. It's something that students will do like throughout, all the way up into senior year, they'll be doing these safety contracts. Again, we just want to remind our students, even though it may be household chemicals that we're working with, that we still always want to maintain that safety. So in science, remember that we only use the metric system. So centimeters, liters, grams, we do not use the English system. So you're not going to be using pounds. You're not going to be using ounces, right? It's only the metric system. And when it comes to selecting tools for your students, we always want to think of what's grade appropriate. So especially for EC-6, right? I really have to think what is it that my students can handle and not break and get hurt, right? So that's something that's super important. So for example, in the early grades, I guess like from kinder to like 3rd or 4th grade, I may not use anything glass, right? In high school, that's all we use is glass everything. But in the lower grades, we want to make sure that we're sticking to plastic items. And in 1st grade, for example, they may not use a microscope, right? But instead they might use like a hand lens, like a magnifying glass type deal. And then in 5th graders, they're going to start using those tools that will actually be measuring really accurately, such as graduated cylinders. But for the younger grades, right, like in 1st grade, it may be more of like just a cup, right? Like I'm just going to measure with a cup, so that they're not actually using measurements, right? Because they're not quite there in terms of the grade level. In 5th and 6th grade, that's when we'll actually start introducing those like more dangerous items, right? Which would be hot plates, Bunsen burners, glass beakers, glass flasks, glass test tubes. Because if they break, right, we know that they'll be okay. They'll just kind of notify us and we'll clean that up. But in the lower grades, they're kids, right? Not as careful. So with the metric system, you do have to know how to do conversions. And so on your sheet, I did put this chart on there that just shows the basic conversion systems. But what's easy about the metric system is all you're doing is moving a decimal. So there's really not any math involved to do a conversion. So if I'm getting smaller, so notice it says that you'll just be moving the decimal to the right, right? As I'm getting larger, I'll move my decimal to the left. And so the way this works is, let's say if I have, I don't know, if I have 2 grams of something, right? And I want to know how many centigrams that is. Well, I would be starting at the base unit because there's no prefix on that unit. So if I have like 2 grams and I want to go to centi, right, I'm going to move 2 places to the right. So I would take my number 2 and I would literally do that, right? So let's see if I can draw on here. Okay, so let's say if I had 2 grams and I wanted to go to centigrams, right? Well, going from the grams to the centi, I'm moving 2 places to the right. So literally that's what I would do. I would get wherever my decimal is, right? My decimal is always at the end of the number, just like a period's at the end of a sentence. And I would just move it 2 places to the right. And then that would tell me that I have 200 centigrams. Okay, so that's kind of how that works. So on your note taker, there are some practice problems there. So if we try that first one there, so I have 125 centimeters. Let me clear this out. Let me clear this. Yes, all right. So we've got 25 centimeters. And then again, because of this C here, right, that's telling me that I'm going to start on the centi. And then it's telling me that we're going to be going all the way to the meters. So I'm starting here and I'm going to move 1, 2 to the left this time. So I have 25 centimeters. And again, my period is always at the end of the sentence. So my decimal is always at the end of the number. And I'm going to go ahead and move 2 to the left. So then my answer is 25 meters.
Miss Hinojos is 125.
Oh, sorry. So then it would just be 1.25. Thank you for that, Alejandra. Okay, so go ahead and try the next problems on your own. Some concentration music for you. All right, so let's try the first one. So Trina, what'd you get for the 1.3 kilometers? How many meters did you get for that one? So if we go from the kilo to the base unit, right, because there's no prefix on this one. So from the kilo to the base unit, how many places would we be moving, Trina?
3.
3, okay. So then I'm gonna go ahead and take my 1.3 and I'm gonna move my decimal. I know where my decimal is now, right, because it's actually there. So I'm gonna take my decimal here and I'm gonna move it 3 places to the right. So 1, 2, 3. So what do we get as our answer?
So then we move the decimal to the end. So it's like 1300.
Mm-hmm. So with the numbers, right, I take whatever I have. So we have 1.3 kilometers. We said we were going to move that 3 places to the right. And so whatever places there's nothing there, you know, if there's nothing there, then I'm just going to go ahead and fill those in with zeros. So the same thing if I was moving my decimal the other way, right? So let's say, for example, I don't know, if I had 1.3 and I was having to move it 3 places to the left, then whatever I'm not filling in, like these little valleys here, I would go ahead and I would just fill in with zeros. So that's kind of how that works. Okay, so our answer for this one, for the 1.3 kilometers, because we moved 3 places to the right, our answer is going to be 1,300 meters. So that should be our correct answer. Okay. All right, so let's try the next one. So 210 meters, how many millimeters do we get? Michael.
Sorry, I had to get to my mute button. 210,000 millimeters.
210
Moving,
millimeters. All right. How many?
moving 3 places to the right from the basic unit to millimeters.
Correct. So again, this is our base unit. The meter is a base unit because there's no prefix on it. The base unit has no prefix. So if I'm going from the base unit over here to the millimeters, I'm going 1, 2, 3 to the right. And just like Michael said, I'm going to go ahead and my decimal point would be at the end, even though I don't see it, right? I know it's at the end of the sentence, just like, you know, a sentence is, right, in a period. And I'm going to move that 3 places to the right, and that's going to give us 210, 1, 2, 3,000. Okay, so that should be our answer for that one. Okay.
On the next one, how do you know if it's Deca or Deci? Because it's DM.
Oh, you're right. Sorry. So typically you won't see those, but I want to say the Deca, they put a capital D, but it's typically you won't see those ones. So the ones that you'll usually use are going to be kilos, deci, centi, and milli. So it's there as a placeholder, but it's not something that we usually measure with, commonly measure with. But good question. Okay, so for this next one, 4.3 decimeters, I'm at this one right here. Alejandra, how many places are we going to move and which direction?
We're gonna move right, and it's just 1. So it's
Correct.
gonna be 43.
Correct. Yes. So our correct answer for this one would be 43 centimeters. So the way that I memorize this, because obviously when you go to take the test, you won't have the chart, right? So the way that I memorize that is by using a little play on words here. And I always forget what these things are called. What is it? It's not a, oh my gosh, I can't remember what it's called. Anyways, so I use King Henry died by drinking chocolate milk. So I remember that. And that helps me to remember the order of the units. So when I take a test, literally that's what I do is I write down the letters, right? So King Henry, right, died by, I just write the first letters, but that's how I remember the order of the letters. And then that tells me which direction I'll be moving things. Okay, so that's kind of how I do that. I wrote them here, obviously on the side going top to bottom, but I always write them the way they are written here. So from left to right. So K, H, D, B, D, C, M. And then from there, based on whatever they give me, now I know which way I can move my decimal point. Okay, so that's just a quick way to remember that. All right, so in science, we measure things, and you know, there's going to be cases where we're going to be measuring things correctly, or, you know, we're not going to be measuring them the same. So there are these terms that we use, which are precision and accuracy. And when in like the real world, right, when we're talking about things in general, the terms precision and accuracy, we always kind of use them the same, right? Like they mean the same thing. But in science, they're different. So for science, precision just means that measurements are close to each other. So a way that we can ensure precision when we're doing a science experiment is whoever is measuring, they're always the one measuring, right? Like if I'm measuring mass of something, and you know, I'm in a lab group and Michael's my lab partner, then and Michael's like, I want to measure. Okay, well, you're going to measure every time we measure, because if not, I may measure a little, right? And the same thing's going to happen with your kids. You're going to have kids who may measure things different ways. If we're looking at volume, like on a graduated cylinder, they may not be reading it correctly. And so then we don't end up with precise measurements. Okay, so precision just means how close they are together. Accuracy means that we're doing it right. Okay, accuracy means that we're getting the right answer. So again, if I'm thinking of my students, right, if I have a student that understands, you know, like how to use the balance or how to use the scale, you know, then we know that we're going to have accurate measurements. But if my students don't know how to do that, even though they may be precise and they may be getting the same measurements every time, they may be doing it wrong every time, right? So we have to teach our students how to measure things with a ruler, you know, when it comes to a scale or even measuring volume. We have to teach them how to do that correctly so that they can always get accurate results, not just precise results. And so when it comes to error, there's always going to be error. Like we're never going to do a science experiment and get things exactly right the way they should be. If I do a calculation and then I actually do the experiment, I'm always going to get something a little bit off, right? And error could be caused to all sorts of things. So one of the main reasons for error is going to be human error, right? We're human, we make mistakes, things just might not, be measured perfectly. But other things could be due to mechanical error. Maybe your balance isn't working. Maybe the way they made your graduated cylinder was wrong, right? Maybe the measurements aren't quite right. So that would be ways that we could get error. Okay, but so with the picture, this just kind of shows you, the differences between precision and accuracy. So I can have one or the other, or I can have them both, right? It just kind of depends on the situation. But what we're trying to do, we're always trying to aim for that precision and accuracy. We want measurements to be as close to each other as possible, and we want them done right. But, as long as we are getting our students to do precision, that's okay. As long as we get them to make sure that they're doing it the same way every time, that's fine. All right, so competency 2 just has to do with science in, just I guess scientific inquiry in general. And so with our students, especially with the younger ones, we need them to understand that science is not, it's different from the other subjects because it's not like something that's like set in stone. So like, for example, for social studies, right? If we're learning about like history, we've got dates, we got facts, like there's nothing that's going to change that, right? But with science, science is always changing and it's always evolving. And even though we may have data to back something up, nothing is ever like, this is the one and only way, and this is exactly correct. So it's always changing. And with science, students, a lot of times we'll see that is only happening in the classroom, right? I do science, but science is something that's happening all around them all the time. So with our children, they're going to have these ideas of what's correct in their head, right? So based on their world, their home and all that, they may hear things, they may see things, their parents may say stuff, their grandparents, right? And so that's truth for them. So when we bring them into the classroom, what we need to do is do experiments with them to show them the truth, right? Because if I tell them like, oh, well, no, your grandma said this, but that's not right. This is correct. They're going to be like, no, like, who are you? I don't care if you're the teacher. My grandma, she knows everything, right? So we want to make sure that we actually show the students the science. So we actually we need them to partake in experiments. Like they have to see it for themselves and do it for themselves in order for it to become truth in their head, because they're not going to believe us otherwise. Okay, so that's something important with the elementary kids is that's what we want to do, is we need them to see those things, test them out, come up with their own conclusions on their own. So these are some important science concepts that you do have to know. And these are, if you'll notice, right, they don't say, well, they're never going to say truth, right? Or like absolute, right? But a lot of times you'll see theory. So a theory just means that it has been tested out, time and time again, and there's nothing that refutes it otherwise. But who knows, right? In 100 years from now, who knows where we may be with technology, right? So for now, it's just a theory, and that's what it will always be. So cell theory just basically says that anything that's living, regardless of its size, all the way down to the smallest bacteria, they're all going to be made out of cells, and everything comes from cells. So things don't just appear, right? So like going back to before cell theory, people think they used to think that people would get sick because of, something just like something just happened to you, right? Like there's no reason for it. There was no cause. Like, I guess you're just unlucky, right? That's what happened to you. But after cell theory, they realized that everything was related to cells. And so if you got sick, it was because of bacteria that you got from someone else. So after this cell theory idea came around is when we had huge changes to hygiene, people washing their hands and all of that, because now they realized that the stuff was coming from somewhere. So then the other idea is plate tectonics. And so with that one, we want to remember that originally all of the land masses on the planet, they started from Pangea. So it was one big landmass, and over time and with the plates moving on Earth, they slowly separated, and that's how we got all of the continents that we have today. Okay, so that's plate tectonics. And the plates are still moving, right? And that's why we have our mountains. That's why we have volcanoes. That's why we have earthquakes. It's all because of those plates that are moving. The next one is going to be Newton's laws of motion. And we're going to talk a little bit more about those in detail as we get to it. But the first law of motion basically just says an object at rest will remain at rest unless acted upon. Acceleration is produced when a mass is acted on by a force. That's Newton's second law. And then for the third one, for every action, there's an equal and opposite reaction. So we'll take a look at those because those are also going to be found in one of the physics competencies. And then the last one, universal gravity. So every object in the universe attracts every other object along their line of centers. So that's how the planets are going around the sun, right? Because of the gravity of the sun, it's so big and so massive that it's able to keep us in its orbit. Us as on Earth, you know, we are so massive that we're able to keep the moon in an orbit around us. But you, me, your pencil, your cell phone, all of those also have gravity. Okay, so everything that has mass is going to have gravity, and everything's always pulling at each other, even though we don't feel it because we're so small. Okay, so on your sheet, it's got a little place for you to just kind of draw a picture to kind of help you remember what those terms are. So with cell theory, remember it's just everything's made of cells regardless of the size of it, right? If it's alive, so that includes plants, bacteria, mushrooms, trees, right? All of those, they're all made of cells. And then plate tectonics, this one is referring to that idea of Pangea. So it all started with one landmass and all of them separated. Okay, and then we're gonna talk about Newton's first, second, and third law in a bit. So you'll draw a picture later. And then universal gravity, everything is always pulling at each other, okay, from their centers. All right, so go ahead and move on here. So hopefully I had a chance to just draw a quick little picture to help you remember that. Okay, so competency 3 has to do with just science in our daily lives, right? And how it affects, you know, just things in life in general. So there are a lot of advances that we've had in science, but, you know, just because we're able to do things doesn't mean that we do, right? Just due to like ethics and, you know, society, stuff like that. So just kind of helping students to understand that, you know, we do have technology to do a lot of things, but it doesn't give us the power, right? To be able to do them. Sometimes there are laws that prevent you from doing things, or even just, you know, maybe your religion, right, is telling you that you shouldn't do certain things, even though we're able to do it. So when it comes to science, we always want to make sure that we are considering those factors as well, right? Scientists they can't play God. So there are things that are going to be governing them. And so with our students, what we also want to do is let them know that, you know, whatever they do is also going to have an effect on them. So it does want us to remind them about, you know, making good choices when they're eating and exercising, just to make sure that that's taking care of themselves, because there are effects to that, right? So everything we do is going to have some sort of consequence. So we got to, you know, teach our students that the way we live our lives, you know, not just for our own body, but even, you know, just like for the planet. So recycling, you know, conserving water, things like that, they all have an effect on everything else. And with our students, we also want to make sure that they make good choices for their not only physical, but also their psychological health. So that would also come into the idea of like, you know, they shouldn't be taking drugs, right? They shouldn't be smoking, you know, things like that will be, you know, that can affect them. All right, so here we have some practice questions, and I'm going to pause here. All right, so competency number 4 is going to deal with concepts that are common to all sciences. So regardless of whether we're talking about biology or physics or chemistry. And so again, thinking of science, right? It's just a way that we can view the world to understand how it works. But there are going to be some things that are going to be common across all different subjects in science. So one would be like the scientific method. So if you don't know the scientific method, you know, definitely make sure you look that up. But with the scientific method, it's basically we have a problem. We develop some sort of hypothesis that we can test. We develop an experiment, and in our experiment, we're going to have controls, we're going to have variables, some things that will change, some that will stay the same. We'll actually run the experiment, then we get some sort of data or results, and then we come up with a conclusion. We kind of go back to the beginning and say our hypothesis was supported or it wasn't, right? So that's kind of the scientific method. And that's going to be used in all sciences, regardless of, age level or anything. So there's always going to be variables that have to be controlled in order for you to have a valid science experiment, right? To ensure that we're having precision and all of that. So another thing that you're going to find common in science is going to be models. So science, right, it involves anything and everything around us. And so sometimes things are just too big to see, like the sun, right, or the solar system. I can't actually show my kids that because it's too big, it's abstract. So we use models to help make it more concrete for our students. Same thing with like a cell. A cell is too small for students to see and understand the way it works. And so we can build a model that's going to show our students, how to see that. And obviously, they're not going to be perfect, right? But models are just a really good way to show our students abstract concepts and make them more concrete. Okay, so competency number 5. With this one, we are just looking at the practices that we use to teach our students about science. So just understanding that depending on their age level, right, there's going to be certain things that we can or can't do with them, just because of where they are in terms of their maturity. So that's why there's some experiments you can do with kindergarteners and different ones that you can do with like your 6th graders. And then when it comes to misconceptions from science, it's because students, again, they have these truths in their head. And so we really have to show them the science, right, so that they can actually understand that and it'll become a truth in their head. And so they need to be involved in actual experiments. So it's not enough for us just to talk about it, but we want to make sure that we engage them in it so that they can understand that as well. So with concrete activities, and this goes for everything in the elementary grades. And I know my Head Start people know this, right? But in the elementary grades, we try to make everything concrete, from math, right? You're going to be using some sort of manipulatives to even in English, we want to try to show them what things look like. So the more concrete we can make things, the better, regardless of that subject area. So when it comes to science, we also want to make sure that we show students that science isn't, it's not just for one gender, it's not just for one ethnicity, but anybody and everybody can be a scientist. And so when it comes to what we show in our classroom or the ways that we talk about it, we want to make sure that we're representing that as well. So it kind of mentioned, maybe even having posters right in your room that shows female scientists, right, or scientists of different ethnicities or different cultures, so that students can see themselves as scientists in the future, as well as being scientists in the classroom, because they are scientists in the classroom. So number 6 is dealing with assessment. And so when it comes to assessment, obviously there's a whole bunch of different ways that we can assess students the same way that we would in a regular classroom. So, it could be just a paper test, it could be bell ringers, exit tickets. But in the science classroom, there's also going to be projects that you can have students do. And with a project, that's something you would be grading with a rubric. Lab reports are going to be ways that students can demonstrate their understanding of the scientific method. So with a lab report, it's going to have your problem, your hypothesis, your conclusion and results. And then we can also have students do presentations. So with presentations, you would be having students maybe explain their understanding of a concept so that you can see, if they are actually understanding the science. So again, there can be formal or informal assessments that can be given, but we want to make sure that, of course, we are communicating with our students, as to their results. All right, so next set of questions here. So with competency number 7, this is where we're going to actually get into content. Okay, so Competency number 7 is going to be one of our physics components. And so with physics, there are some different forces that students have to understand. So they have to understand gravity, electricity, and magnetism. And so with gravity, remember we mentioned that concept a little bit earlier. So it's basically everything, right? Anything that has mass is going to be pulling at everything else from its center. So that's our gravity. Electricity is basically just electrons, right, that are moving, and we'll talk a little bit more about that one. And then magnetism is actually tied to electricity, like those two are kind of linked to each other. But when I think of magnets, right, you think of, a north and a south pole, and, you have opposites attracting. So those are kind of those general concepts that you do have to know. So with magnetism, it's just a force of attraction or repulsion, right? Because you can have like charges are going to repel each other, but they have different ionic charges. And so that ionic charge, or those ions, that's kind of how they're related to electricity. So magnets are typically going to be metal. They'll typically have those two poles. So sometimes you see the magnets that are like a U, right? But in the classrooms, a lot of times you'll just see like a bar magnet. And they'll always have one side that's labeled, positive and negative, meaning the north and south. And so when we think of Earth is actually like a really large magnet. And gravity is that magnetic field. So I'm sure you've seen pictures kind of where they have those like, arrows kind of like coming out of the earth, right? And that's how we actually have our north and our south pole. So it's actually that attraction to them that a compass does, because it's attracting us to those different ends of our magnet Earth, I guess you could say. So in order for everything to be held onto Earth, right, we have gravity that's like pulling us down. It's that attraction. But it's also attracting the atmosphere. So even the air, that we have around us right now, even that's being attracted to the surface of Earth because of its pull. So the air, right, is also made up of mass, or it's particles. So it's also being pulled to the center of the Earth. And then when we think of objects, right, the denser objects are, the more gravity they're going to have. So that's why, for example, if you go to the moon, right, when you see people on the moon, they're kind of like walking, like bouncing, right, slow, because there's not as much gravity pulling them down as there is here on Earth. Okay, so the next concept is force and motion. So you have to know position, distance, and displacement. Okay, so those terms specifically. For those of you that are here for 4 through 8, you have to know what the difference is between a scalar and a vector. Okay, so that's kind of how that goes a little bit more in depth. So with position, position is basically just telling you where something's located, right? And when we look at the terms of distance and displacement, they're all in relation to position. So wherever you start, right, if I move somewhere, I can measure my distance or how far I traveled, or I can just look at my start point and my end point, and I can measure the distance between those two places. So for example, I like to go ride bikes with my boys, right? We like to go ride bikes, and we go and we travel around the neighborhood. And so we travel a pretty good distance, but we always come back home. So our displacement is always 0, right? We never go anywhere else. We always, we're going to go around the neighborhood, but we always come back home. So our displacement will always be 0 because we don't go anywhere in relation to the start, or where we're at. So when it comes to scalars and vectors, a scalar is just a number where direction doesn't matter. So for example, when I travel, on my bike, I may be traveling, I don't know, a mile, right? I'm sure we do a lot more than that, but let's say I travel 1 mile. But if I'm using a vector to represent that, I could say that I'm traveling a mile south. Okay, so vector just means that I'm including my direction one way or the other. And so I can include a number depending on how far I traveled for distance, but I can also include a number to say how far I traveled for displacement. So maybe if I drove my bike to my friend's house that lives close by, I may have traveled a certain distance because I had to go through the streets and all that. But if I actually measured, from here to his house, a straight line, my displacement would be less. Okay, and that would be in a certain direction if I was talking about vector. All right, so this one just kind of gives a quick overview of what that looks like.
Today, we will learn about what is distance and displacement. A lot of you will say, both are the same thing, just different words. But no, it's not. So let's know first, what do you mean by distance? It is the total length of path covered by object without specifying its direction. Then, what is displacement? It is the overall change in position of an object in a specific direction with the shortest distance traveled. Or let's say in simple terms, it is the shortest distance traveled in specific direction. Still confused? Let's take one example. Let's say I have to go to my friend's birthday party, and his house is 10 kilometers to east from my house. But here I take different and longer route, as I have to buy gift for him, traveling to about 20 kilometers in total. So here, the destination is same, but the path traveled is different. Then, what is the distance and the displacement of the car here? Come, let's see. So, if I travel straight 10 kilometers to east to my destination, it will be the shortest path I can take. Hence, what are we getting here? When I say 10 kilometers to the east, my shortest path. Yes, correct, it's the displacement, but now, as I have to buy gift, I am taking the longest and the indirect route, with no specific direction, but reach the same destination. So, what we get here? When I travel 20 kilometers, with no specific direction, taking the longest and the indirect route. Yes, it is the distance. Now let's say, if I travel 20 kilometers, from one start point, and at the end, stop at the same point, then, what will be my distance, and the displacement? Here, the car starts traveling 20 kilometers from one point, and ends at the same point. The distance traveled here is 20 kilometers. But the displacement is 0, as the starting point and the end point of the car is same, or say, the origin and the destination of the car is the same. Hope you all understood the distance and the displacement. Hit like and subscribe for more.
Not the best video, but gets to the point. Okay, so the other video that I put in here, I'm gonna keep moving just so that we can finish everything else, but it'll be in the Nearpod so you can take a look at it, but it's also gonna look at graphing. So you have to know what the term is, and you also have to know what it looks like on a graph. Okay, so for distance and displacement. Okay, so then for motion and speed, we have to understand the definition of speed. And so for 4 through 8, you also have to know velocity. Okay, so speed and velocity are basically the same thing, but with speed, you're not including the direction. That's basically the only difference. So with speed, it's the formula for that's going to be distance divided by time. So total distance divided by total time. And you have to know what that looks like on a graph. Okay, so even though this one says velocity, just know that it could be speed. Okay, it's the same thing here. So with speed, it's typically going to be measured in meters or kilometers, right? Because we always want to use the metric system. So it's not something typically that we'll be using like miles per hour, right? Like the way we do in our cars.
What is speed? Speed is a quantity that refers to how fast an object is moving. An object with a high speed covers a relatively large distance in a short amount of time. Contrast to this, an object that has a low speed covers a relatively small amount of distance in the same amount of time. Speed can be thought of as the rate at which an object covers a distance. The average speed is defined as distance traveled over time of travel. To give you an example, meet Tim. Let's say Tim is walking down a sidewalk at 3:15 in the afternoon. 20 seconds later, Tim has traveled 35 feet. At what average speed was he traveling? To find out, we divide 35 feet over 20 seconds, and we find out that he was traveling at 1.75 feet per second. Day by day, we constantly see objects in speed within the world that surrounds us. So, are you ready to calculate speed?
So again, in elementary, it might just be, a real simple calculation that you'll have to do, but you don't have to know any of the complicated stuff. All right, so next one we have are going to be Newton's laws. And so for Newton's first law of motion, we want to remember that an object at rest will remain at rest unless an unbalanced force acts upon it, or the opposite, right? So an object in motion will remain in motion unless an unbalanced force acts on it. So with Newton's laws, a lot of times the examples that they want you to know, and especially in core 4 through 8, they want you to know some of the specific examples, would be like using seat belts in a car. So, I'm sure all of you have been in a car and, hopefully you haven't been in an accident. But if you have been like rear-ended, you move forward, right? And so the reason is because if you're stationary, I got rear-ended a couple years ago, and I was parked at a light, and I got hit from behind, and boom, like I moved forward, right? And that's how people they get hurt on their steering wheels and all that, because their bodies at rest, right? And the object that's hitting them is going to cause them to move. Okay, so I'm sorry, so it's not going to be forward, you're going to be backwards actually, because you're going to be staying in that motionary spot. So if you've ever heard of people that have been in car accidents where maybe they're driving super, super fast and they hit something and people like get ejected from vehicles, right? It's because if the car is going at 60 miles per hour, that's how fast you're going, right, as well. And so if something stops you, your body's going to keep going 60 miles per hour. And that's why people fly out of windshields, for example, because they didn't have their seatbelt on. Or if you've been in an accident and you did have your seatbelt on, you'll end up with these really big bruises, because your body's hitting the seatbelt at 60 miles per hour. So that's Newton's law. That would be in motion. So if I think of something at rest, I'm sure you all have seen that magic trick where they have a tablecloth and it's got dishes on it, and they get the tablecloth and boom, they pull it out, right? And all of the stuff stays there. That would be also Newton's law of inertia, because all of the plates and cups that are on there, they're at rest. And so when you pull the thing out, they stay at rest. They don't want to move. And that's how that trick works. Okay, so on your paper, if you go back to one of those first competencies, there's a little box in there so you can draw a quick little picture to remember what this term means, or this law means. So remember that Newton's first law, it has to do with both an object in motion, staying in motion, and an object at rest and staying at rest. So I would suggest two little pictures, right, representing both of those. And another example of an object at rest with Newton's laws would be like you get like an index card and you like put it over a cup or even over a bottle, and you can put a penny on the top of it, and you just like flick the card away and the penny will just fall right in. So that's also an example of inertia, because the penny is at rest, and even though you move the card out of the way, the penny doesn't want to move, it just wants to stay there, so it'll fall in. So it's like a common experiment you do with kids for that one. Okay, so Newton's second law has to do with force, mass, and acceleration. So for those of you doing the 4 through 8, you have to know how to calculate. So there are going to be calculations you're going to have to do. So you are going to know, so you would need to know the units. For force, you've got newtons, mass would typically be grams, and acceleration would typically be meters per second squared. So that's the general formula, but the general idea, so those of you doing EC-6, you just kind of have to know the concept. So basically, like the bigger an object, the more force you're going to need to be able to move it, and vice versa. So with acceleration, what that definition actually means is it's a change of velocity. So basically making something move would be a change in velocity, whether you're making it move faster or slower. Okay, and then we're going to watch a little video so you can just kind of get a better example on that one, but it's with it's going to show you with a bicycle. And I think that makes a little bit more sense for Newton's second law. For Newton's third law, this is action reaction. So that's typically what the laws refer to, the action reaction. And so for Newton's third law, for every action, there is an equal and opposite reaction. So for example, here with the balloon, right? If I let the end of the balloon go, the air in the balloon is actually going to be pushing out, and it's going to cause the balloon to move in the opposite direction. So it's actually pushing on the air in the atmosphere, and that's why it's moving in that direction. It's not that air is just pushing it in one way. It's actually that it's pushing on the air, and the air itself is pushing it the other way. So there's always two forces involved. So for those of you doing 4 through 8, you always have to know that there's going to be two forces. There's going to be those two vectors, which would be two arrows showing you those different forces that are happening. For EC-6, basically just knowing the concept. So for here, when she's pushing off on the on the wall, she's going to move in one direction in the water, but it's actually because the wall is pushing her. Okay, so that's why we want to think it's always two forces, one in the other. So this is an example of how rockets are able to launch up into space, right? So they're pushing down, and it's the ground that's like pushing up on them. This is how you're able to row a boat, or if you've ever been swimming, right? And you move your arms that way. So I push backwards, but the water actually moves me forwards. Okay, so this one's going to show the Newton's 3 laws. And then again, on your paper, you have a place to draw a quick little picture for each of them.
Have you ever noticed that it's harder to start pedaling your bicycle than it is to ride at a constant speed? Or wondered what causes your bicycle to move? Or thought about why it goes forward instead of backwards or sideways? Perhaps not, and you wouldn't be alone. It wasn't until the 17th century that Isaac Newton described the fundamental laws of motion, and we understood the answer to these 3 questions. What Newton recognized was that things tend to keep on doing what they are already doing. So when your bicycle is stopped, it stays stopped, and when it is going, it stays going. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest. That's Newton's first law. Physicists call it the law of inertia, which is a fancy way of saying that moving objects don't spontaneously speed up, slow down, or change direction. It is this inertia that you must overcome to get your bicycle moving. Now you know that you have to overcome inertia to get your bicycle moving, but what is it that allows you to overcome it? Well, the answer is explained by Newton's second law. In mathematical terms, Newton's second law says that force is the product of mass times acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. And the more mass your bicycle has, and the more mass you have too, the more force you have to use to accelerate at the same rate. This is why it would be really difficult to pedal a 10,000-pound bicycle. And it is this force, which is applied by your legs pushing down on the pedals, that allows you to overcome Newton's law of inertia. The harder you push down on the pedals, the bigger the force, and the quicker you accelerate. Now on to the final question. When you do get your bike moving, why does it go forward? According to Newton's third law, for every action there is an equal and opposite reaction. To understand this, think about what happens when you drop a bouncy ball. As the bouncy ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball with the same force, but in the opposite direction, upward, causing it to bounce back up to you. Together, the floor and the ball form what's called the action-reaction pair. When it comes to your bicycle, it is a little more complicated. As your bicycle wheels spin clockwise, the parts of each tire touching the ground push backwards against the earth. The actions. The ground pushes forward with the same force against each of your tires. the reactions. Since you have two bicycle tires, each one forms an action-reaction pair with the ground. And since the Earth is really, really, really big compared to your bicycle, it barely moves from the force caused by your bicycle tires pushing backwards. But you are propelled forward.
All right, so good example there. And then I did put, there's another video in there. So it also just explains Newton's laws again, a little bit more thoroughly, but it would be better for the 4 through 8. So it'll helpful for EC-6, but it does get in a little bit more depth for 4 through 8. Okay, so then with physics, you also have to understand simple machines and understand how they affect force, okay, deal with force. So for the 4 through 8, there are some formulas that may be involved with simple machines, especially with pulleys. So for all simple machines, all they do is they change the direction of the force. And in some cases, they may require less force. So for example, if you've ever had to, carry something up, I don't know, up some stairs, right? It's going to require a lot of force to move that up there. But if you were able to just like push it up a ramp, it's going to require less force, right? It may be more distance that it'll end up traveling, but ultimately it's going to be doing the same amount of work. So when we think of work, and that's something that 4 through 8 has to understand, there's a formula to calculate work. It has to do with the force and the distance that something is moved. So again, if I'm thinking of this person here trying to move this onto the truck, right? If I had the box on the floor, like next to the truck, and we're moving it up, the work would be exactly the same as if I was using a ramp to push it up. So the general idea is that a simple machine is going to cause us to do the same amount of work, but it's going to cause us to do it with a different amount of force. So when we look at a wedge is basically just I'm pushing a downward force, but it's actually causing the force to move outwards, right? And that's how you're kind of able to crack like a piece of wood open, or even just use a knife. So I'm pressing down, but it's actually causing the force to go sideways. When we have a lever, there's different types of levers, but the general idea, right, is that you have something long and it's just changing the direction of the force as well. A wheel and axle, we use those all the time. In your car is an example of you got wheels, so that'd be a wheel and axle, the door handle, anything. Basically, I turn, right? I'm turning it and it's causing the force to be, changed as well. With a screw is basically just an inclined plane, but it's wrapped around something, right? So that's all a screw is. Same thing, changing that direction. And then a pulley is going to be changing the direction, but I can do multiple pulleys. So for those of you doing core 4 through 8, there is a formula that can be used to calculate the amount of force that will be changed using different amounts of pulleys. So there's like, it's a little bit more complex than that. So then when a complex machine, when we talk about that term, it's basically just 2 or more simple machines. So like a bike, for example, would be a complex machine because it's going to have, it's got wheel and axles. It's going to have pulleys on there, right? It's going to have like different things.
Clarendon Learning explores simple machines for kids. Hey kids, in the beginning, everything had a beginning. Think about it. Huge bustling cities started out as little towns with little buildings. We wouldn't have supercars if Carl Benz hadn't built his first motor wagon. And we never would have gone to the moon if someone hadn't invented the wheel. The wheel and axle is an example of a simple machine. And this is what we're going to explore today, simple machines. Let me introduce you to some important helpers of mine. We call them simple machines. The incline plane, the lever, the wedge, the screw, the wheel and axle, and the pulley. These tools have made the work I do so much easier. I'd like to show them to you, and I'd like you to use your imagination. Are you ready to learn about simple machines? Awesome! Let's go! Keep in mind that a simple machine has few moving parts and should enable you to do more work with less effort and energy. Look at this person hoist a sail with a simple machine. She's doing more work with less effort. She's crossing the ocean with a simple machine. This is the incline plane or ramp. It can be used to lift heavy objects from a lower level to a higher level. How much do you think this dump truck weighs? It weighs around 628 tons. That's 1,256,000 pounds. Whoa! And this incline plane is helping this machine get from a lower level to a higher level with the greatest of ease. Using a gradual ramp enables you to travel up and down much easier. And using a ramp is the way that a person in a wheelchair can get up over a curb or into many buildings with multi-levels. Maybe the ancient pyramids of Giza were built using the inclined plane. I wonder what other simple machine might make good use of the inclined plane. Hey, how about the wheel and axle? Yeah, moving equipment up and down a ramp using wheels is easy. The wheel and axle are used all over the world for all sorts of things. Here's an example of my friend, Mr. Pottery Man. I wonder what he's making. I bet it's a cereal bowl to hold a lot of cereal. And what's he using to make that cereal bowl? You're right, a wheel and axle. Good job. The wheel is probably the greatest simple machine of all time. Think of everything the wheel can do and what we use it for. Just about everything in the world moves because of the wheel. Planes, trains, automobiles, bicycles, unicycles, wagons, horse carts, pickup trucks, hand trucks, wheelbarrows, skates and scooters. Wait, whoa, back up. Is that a 6-wheeled truck? Whoa! The wheel and axle have made the work we do easier and recreation more fun. I mean, how fun would a bike be with square wheels? Next, if you give me a fulcrum or a pivot and a plane, I'll give you a lever. Actually, 3 types of levers, depending where you put the pivot. Some examples of the lever as a simple machine are scissors, pliers, a baseball bat. Your arm and elbow is a good example of the lever. The lever gives us leverage to move things. A teeter-totter is a super fun, simple machine. Just ask Lily and Max.
Hi. Hello, friends.
The shovel is a combination of 2 simple machines, the lever and the wedge. Yes, the wedge is a simple machine and very powerful. With the wedge, I can split wood. With a knife as a wedge, I can cut through steaks and chicken and vegetables with ease. I like the wedge. I can use it as a doorstop and keep my door open. A nail is another example of the wedge, a very small but important simple machine. Look at the screw, a simple machine all by itself. With the screw, I can attach things to a wall. I can drill a hole. I can seal a bottle with a screw-on cap. And the spiral staircase? Yep, a screw. What about curly fries? I don't think they're a simple machine, but these sure do look yummy, and I'm getting hungry. But the screw is a very cool simple machine. Which brings us to the final simple machine. Last of all, but not the least of all, the pulley. The pulley is like a wheel but with a groove. With a couple of pulleys and a rope, you can exhibit superhuman strength. Look at this example of Mr. Kitty getting pulled up by a pulley. Look how huge that crane is. A lot of huge buildings all over the world are built by cranes. A simple machine. The elevator uses the simple machine technology of the pulley. And who loves elevator rides? I do. We just learned about the 6 simple machines. Do you remember what they are? The incline plane, the wheel and axle, the lever, the screw, the wedge, and the pulley. Great job! These are the simple machines. They're around us every day. And when you assemble several simple machines together, you get cool things like cars, airplanes, and roller coasters. The bicycle uses many simple machines. Can you figure out what they are? Can you see the wheel, the lever, and the pulley? Good job! Today's assignment is to look around and identify the simple machines in the world around you. And while you're at it, check out the Clarendon Learning activity pages made for your grade level. Thanks for following Clarendon Learning. Be sure to subscribe.
All right, simple machines. Okay, so next up we have physical and chemical properties. So with, oh, sorry, hold on. Let me make sure I didn't miss anything. No, okay. So with physical properties, this deals with our chemistry concepts here. So one thing we want to remember is that when it comes to chemistry, right, we talk a lot about matter. And so matter is just anything that has mass and takes up space. Anything, pretty much everything is going to have matter. Even the air, the air that we breathe is made up of matter. And the way that we measure matter is by using mass. So that's why we're going to be using grams, and that's why we use a scale. So when you go and you step on your scale at home, that's actually measuring your weight, and it's actually looking at how much gravity is pulling down on you. So if you wanted to lose some weight, you could go to the moon and you'd weigh a lot less. So there's going to be a lot less gravity on the moon, and so your weight will be different up there. But if I were to measure my mass here and measure my mass on the moon, it's going to be exactly the same because I'm made of the same amount of matter. The other term that we'll use is going to be volume, and volume is basically just describing the amount of space that matter takes up. And so when we look at our states of matter, right, solids, liquids, and gases, they could possibly, right, I could get 3 possible samples that all have the same amount of mass, but they could have a different volume depending on how far apart the molecules are separated. So when it comes to our solids, the particles are just so close together that they hold their shape, right? With a liquid, they're close enough to be touching, but they can't hold their shape. And then in a gas, they're separated as far apart as possible from each other. So that's typically why we don't see the gases, right? Because they're so far apart. Okay, so this video just kind of talks about the different states of matter. So I'll leave that one for y'all to take a look at later. So then when it comes to matter, matter is going to be composed of, the simplest component of matter is going to be elements, and all of your elements are going to be found on the periodic table. Okay, so on the periodic table, those are the only elements that we have. This table looks like it might be a little bit older, so I think there's a couple more that are missing on this one. But with the periodic table, this is changing. So I'm sure when you all were in high school, the periodic table looked a little bit different. Some of these elements are man-made, so that's why the periodic table may, depending on where you look, they may have different amounts of elements. But this is the simplest amount of matter that it can be broken up into. And so when we think of an atom is going to be made up of protons, neutrons, and electrons. When it comes to thinking of the terms of molecules and compounds, a molecule is basically just when elements are going to be covalently bonded together, meaning that they're sharing electrons. And in compounds, they're going to be ionically bonded. Ionically bonded, meaning that they're like attracted kind of like by opposite poles, because there's like a give and take of electrons. So for EC-6, right, it's basically just knowing like what these definitions are. For 4 through 8, it's knowing a little bit more in depth in terms of like what covalent bonding is, and what ionic bonding is, and how to form those like molecules and compounds. So just a little bit more challenging there. And also knowing if you have an atom, how many protons, neutrons, and electrons that they have. Okay, so this one just kind of talks a little bit about that.
In this video, you'll learn the difference between an element, a mixture, and a compound. Firstly, some definitions. An element is a substance that cannot be broken down into anything simpler. A mixture is a substance consisting of two or more substances mixed together, not in fixed proportions and not chemically bonded. And a compound consists of two or more elements chemically combined. So consider the two elements iron and sulfur. We should perform 4 tests, firstly on iron and sulfur separately, secondly on a mixture of iron and sulfur, and thirdly on a heated mixture of iron and sulfur. The 4 tests we are going to do are appearance, action of water, action of an acid, and finally action of a magnet. So starting with performing the tests on iron and sulfur separately. Iron filings are dark grey crystals, whereas sulfur is a bright yellow powder. You will see that the iron sinks and the sulfur floats. With iron filings, you can see bubbling. The iron reacts with the acid to produce hydrogen gas, which can be tested for by holding an empty tube over the tube of iron filings and acid. After a short time, we remove the upper tube and immediately put a lighted splint to the open end of the tube. A pop is heard indicating hydrogen gas. With sulfur and hydrochloric acid, there is no visible reaction. If the iron is sprinkled onto a sheet of paper and a magnet is moved underneath the paper, you will see the iron filings follow the magnet as they are attracted to it. When the same is done with the sulfur, you will see that the sulfur is not attracted to the magnet. So from these 4 tests, it can be seen that iron and sulfur are 2 completely different elements and behave differently in the 4 tests. Iron is a metal element, sulfur is a non-metal element. So now let's look at performing those same 4 tests on a mixture of iron and sulfur. So some iron filings and sulfur powder are mixed together on a piece of paper, and we now have a mixture of iron and sulfur. If we add a bit more iron and mix, we still have a mixture of iron and sulfur. We could add a bit more sulfur and mix. It's still a mixture. As said earlier, the components of a mixture, in this case iron and sulfur, are not in fixed proportions. So let's now perform those same 4 tests on the mixture of iron and sulfur. In the mixture, we can clearly see the dark grey crystals of iron and the bright yellow powder of sulfur. We can see that the iron in the mixture still sinks and the sulfur floats. The components of the mixture have separated. The iron in the mixture reacts to produce hydrogen gas as before. It gives a positive pop test when mixed with air and the mixture ignited. The sulfur in the mixture, however, gives no visible reaction. As the magnet is moved underneath the paper, you will see that iron is attracted, but the sulfur is not. Again, as in the test with water, the iron and sulfur can be separated, illustrating the fact that the components of the mixture can easily be separated by physical means. From these 4 tests, it can be seen that the components of a mixture behave in the exact same way as they did when they were on their own. That is, they retain their separate identities. Finally, let us perform the same 4 tests on a heated mixture of iron and sulfur. For this, we need to carefully select our amounts of iron and sulfur. If the mixture of iron and sulfur is heated briefly and then removed from the flame, a red glow spreads throughout the mixture which turns black. Heating the mixture causes the iron and sulfur to bond chemically to form the compound iron 2 sulfide. This can be shown by the equation. Now let us look at how the compound iron 2 sulfide behaves in the 4 tests. It's a black solid, different appearance to either the iron or the sulfur. It all sinks, there is no separation. The reaction between the iron 2 sulfide and hydrochloric acid should be done in a fume cupboard, as when the hydrochloric acid is added to the iron 2 sulfide, bubbles are seen, but the gas formed is hydrogen sulfide gas, which is toxic. As the magnet is moved underneath the paper, you will see that the iron 2 sulfide is not attracted as it is not magnetic, so we cannot separate the heated mixture. However, as often happens in class, if the wrong amount of iron or sulfur is used so that there is excess iron, then the iron 2 sulfide will be attracted to the magnet because of this too much iron.
Okay, so I think that did a good job of explaining the way that they are different. So you do have to understand the differences between elements, compounds, and mixtures, and whether they can or cannot be separated. So with an element, you can't separate it any further. With a compound, you can't separate it any further, but with a mixture, you can. Okay, and you can separate it by physical means. So the way that they were testing all of those 3 different examples that they used was based on their properties, right? So a physical and a chemical property, they're just ways that are used to describe matter. So for example, the first thing that she was looking at was the color, right? So looking at what color they look like. In all 3 of them, we could see, you know, what the colors were. That's a physical property. So it's just, when I think of physical properties, I would always tell my students, use your 5 senses, right? So that's, if I want to describe something, I can describe it using my 5 senses. But there's also some other science terms, right, that we could use, such as hardness or luster or conductivity. And all of those are just describing matter. With a chemical property, we're looking at how matter reacts to other matter. So for example, in the video, when we were looking at a reaction, it was with the hydrochloric acid. So when she reacted them with the acid, we were looking to see if they reacted. So for the iron, it did react, right? So there was a reaction, but with the with the sulfur, there was no reaction. That's still a way to describe it. That's still a chemical property. I'm still saying it doesn't react, okay? So those are the 2 terms for properties. So property, remember, that's just describing matter. Okay, and so when it comes to properties, so there are some pictures here. So we're gonna watch again, another little video that just kind of talks about properties, but it's just ways to describe it. The next one that we're going to look at are going to be changes. And so with physical and chemical changes, my students would always confuse those because they sound the same, right? But remember, properties, it's describing, okay? Just a way to describe matter. So as we're watching the video, and if you, you know, right now already have some ideas, make sure that you are drawing a little picture of what a physical property is versus a chemical. All right, so that's how we use properties. They're used to describe things or to figure out the identity of something. So that's typically how they would be used in the classroom. And so when it comes to changes, we're looking at something like before and after. Okay, so with a physical change, it's going to be a change in a substance that does not change the original composition. And so just to clarify, because this is a misconception that happens in the classroom too, is teachers tell students physical change is, I know it's a physical change because I can change it back, right? And so then students come in with that misconception. But if I crack an egg open, I can crack the egg and that's a physical change, but I can't put the egg back together, right? So that could be, that's how that's a misconception for the students. And so don't think of it that way. So a physical change means that I changed it, but it's still just the same thing, right? If I crack an egg open, I still have an egg, right? A cracked egg. But when we have something that undergoes a chemical change, I'm turning it into something new. Okay, so there's a new, you know, it's new completely. So if I actually cook the egg, I'm gonna notice a change in color of the egg. The clear is gonna go to white. It's gonna smell differently. Right. And so there's going to be indicators that are going to tell us whether something is a physical or a chemical change. So these indicators are going to be our best bet to help us determine whether something is physical or chemically changed. So for example, when you light something on fire, right, if I burn like wood, I'm going to be seeing a change in color. So I'm going to go from whatever color it was originally to black. We're going to have gas produced. So you'll be able to see smoke coming out of it. There'll be a change in odor. So it's going to smell different from beginning to, you know, when you actually burn it. And you'll actually have a production of heat when you burn something. So all of those are going to be indicators. So if it doesn't change color, doesn't produce gas, you know, doesn't have a change in odor, doesn't produce heat, then I know that it's a physical change. Unless I'm adding color, right? If I mix like Kool-Aid powder into water, that's a physical change because it's still just Kool-Aid powder and water, even though I had a color change, but it's because I was adding the color. All right, so in your notes, make sure that you do, you know, show an example of a physical change versus a chemical change, or a way for you to remember that. And then this video kind of gives us some more examples.
No matter where you are or what you are doing, things are changing all around you. Whether it's plants growing or logs burning, or even if you're just eating food. The materials around you are changing in size, shape, and structure, releasing or absorbing energy, and creating new substances. In chemistry, most changes are divided into two categories: physical changes and chemical changes. A physical change is something that changes the physical properties of an object or substance, like size, shape, or form. Cutting a piece of cloth is an example of a physical change. Even though the cloth changes shape and size when it is cut, it does not create a new substance. It's still cloth. Even if the pieces of cloth are sewn together and made into a shirt, only physical changes have occurred. The shirt is still made of the same substance as the original cloth, just in a new form. Another type of physical change involves changing states of matter, and water is a great example of this. Ice melts and becomes water, and water evaporates to become steam. But no matter its form, the water is still water. One way we can tell this is a physical change is that the change can be undone. Water vapor can condense back into liquid water, and liquid water can be frozen back into ice without changing to a different substance. In fact, many physical changes can be undone. For example, we know that dissolving sugar into water is a physical change, because even though the sugar and the water are mixed together, they do not combine and create a new substance. They are still just sugar and water, and they can be separated from each other. Not all mixtures are as simple to separate as sugar and water. When you mix butter, sugar, flour, and eggs, there is not a practical way to separate them again, but it is still only a physical change. The chemical change occurs when you put your mixture in the oven and add heat. Baking has many of the indications of a chemical change. The mixture in the oven absorbs heat. It also changes color and produces an odor. Gases are released, which is what helps the baked goods to rise. Finally, this change cannot be undone. You can't unbake a cake. Chemical changes occur when the particles of two or more substances are rearranged to form a new substance. For example, when you burn wood, the wood is transformed into a new substance: ash. Just like in baking, this change cannot be undone. Also like the cookies, the wood changes color, releases gases, smoke, and produces an odor. Unlike in baking, this chemical change releases heat and gives off light. Chemical changes take place all around us. Metal rusting, fireworks exploding, fruit ripening, and digesting food are all examples of chemical changes. Here are some clues to look at if you're not sure whether something is a chemical or physical change. Chemical changes always form a new substance. They may absorb or release heat. Sometimes a chemical change will cause a change in color, produce an odor, create a sound, release gases, or produce light. Chemical changes usually cannot be undone. Physical changes do not form a new substance. A physical change may change the shape or size of an object. It may change the state of a substance's matter. Many physical changes can be undone in some way. In a physical change, you end up with the same substance you started with, even if it looks different. I hope you enjoyed learning about physical and chemical changes today. Look around and see if you can identify the physical and chemical changes around you. Goodbye till next time.
right, so let's go ahead and try out some problems. So with competency number 9, now we're looking at energy. So this one is kind of getting into our physics again. So with energy, what we want to remember is that we do have the law of conservation of energy. Just like in chemistry, which I forgot to mention, we have the law of conservation of mass. Okay, so basically that just means that mass is not created or destroyed. It's conserved, meaning it just changes form. The same thing happens with energy. So we only have a fixed amount of energy, and that's just always changing form. So there are different types of energy. Here, it kind of gives you some examples of the way you might see them, right? So there's light energy, heat energy, chemical, kinetic, electrical. Sometimes instead of heat, they may say thermal, right? Thermal energy. There's, when we think of kinetic and potential energy, there's going to be energy in motion, and then potential energy is going to be any type of stored energy. So for example, chemical energy is a type of stored energy. Chemical energy could be in the form of a battery, right? That's just basically stored, and then when I plug it into something, it's going to work. It could even be food. When you eat food, it is stored energy, but once I put it inside of my body's going to start to break it down and then turn it into energy that my body can actually use to make me move. So when we think of energy being transferred, we want to think of how that energy is being transferred from one thing to another. So for example, if I have a toaster, right, I'm going to plug my toaster into the wall, and I'm going to take that electrical energy and I'm going to turn it into like thermal energy, right? Maybe even light energy. So when I put my bread in there and I turn it on, I'm going to feel it get warm. I'm going to see the light turning on, inside of it as it's heating up. And then that energy is going to, heat up my bread or something. And then if I take my bread out, I'm taking that potential energy, right? Chemical potential energy, and I'm going to eat it. So those are kind of just looking at how that energy can be transferred from one thing to another.
Most people would say that this car has a lot of energy because it's moving. But where is the energy here when the car is stopped? Pause the video while you think of an answer. If you chose "it's been used up," you're using the word energy in its everyday meaning. If something has energy, we think of it as being able to do something useful, a sort of fuel value. As this is used, we have to come back for more fuel, or pay for more electricity. So with the car, where is the energy here? Many people would say it's in the petrol, but the petrol needs oxygen from the air to burn, so the energy is stored whilst the petrol and oxygen are kept apart. This chemical store is just one way of storing energy. Here are some more. To be useful, energy has to be transferred using energy carriers. Mechanically, for example kicking a football. Electrically, for example when using electricity at home. By heating, for example when cooking on a stove. Or by radiation, for example light and microwaves. Let's see how this works. Imagine cooking using a camping gas stove. The energy stored in the butane and oxygen system is transferred by heating to a thermal store in the pan of water. However, some heat is wasted, so this is better. Now imagine using a battery-powered drill. The chemical store of energy is transferred electrically to the motor, which transfers it mechanically by the movement of the drill to a thermal store as the drill and the wall get hot, and a little also is transferred by sound waves, which also heats up the brain and environment as the sound vibrations are absorbed. We can use Sankey diagrams to show that the total amount of energy, measured in joules, is constant in any change, but some always gets wasted. Here is our camping gas stove. Note that the width of the input energy, 100 joules here, is exactly the same of the sum of the output widths here. But for now, remember that in all changes, energy, measured in joules, does not get used up. Energy is conserved. However, energy becomes less and less useful, ending up as an environmental waste heat. So we always have to come back to an energy source for more. Note that we also talk about conserving energy sources, which means simply being careful with them and not to use them too quickly. Find out more about energy resources in this video.
Okay, so that's energy conversions, right? So then next we have to think about heat energy in general. So when we talk about temperature, temperature is basically just a measure of the kinetic energy in a molecule, in a substance. So for example, if I have a glass of water and I put a thermometer in there and I'm trying to get the temperature of it, I'm actually measuring how fast the water molecules inside of there are moving. And it's kind of weird to think of, right? But there's actually movement in there that's causing the temperature to rise. So when we think of heat, heat is just the total energy that atoms or molecules have. And then we want to remember that the sun is the source of all energy on the planet. So that's why, for example, in that previous question, when we talked about that ash, the volcanic ash, if we have a blanket of something covering the earth, right? Even though the sun is out there, if it can't get the sun rays in, then it's not going to be able to heat up the earth. So the sun is that like where all the energy starts. And the sun is going to be transferring its heat to the planet, and plants are going to start getting that energy for us. So when we think of, organisms eating other organisms and how we all get energy, right? It's all going to start with the sun, and it all gets to the plants first. So our plants will use the sun to do photosynthesis, and that's how they make their own food, right? Which would be sugar, which would be chemical energy or glucose. And then once the plants are eaten by another animal, that's kind of how that energy is going to be transferred. So if you are a vegetarian, all you eat is plants, right? And so that means that the sun gives the energy to the plants and you're getting all your energy from those plants. Most of us, we eat meat, right? So we're going to be eating, if I like to eat steak, right? I'm eating a cow. The cow is a plant eater, so it actually ate those plants, right? And the plants got their energy from the sun. So we're all connected to the sun in one way or another. So when we talk about heat and heat being transferred, there are going to be three main ways that heat will be transferred. So there's conduction, convection, and radiation. And with conduction, it has to do with like two things touching each other. So conduction is going to be the transfer of heat through a solid. So for example, they say that if there's a fire in your house, right, before you open your door, you should go and touch the door. So if you touch the door, right, using your hand, you're going to be looking for heat transfer due to conduction. And so if you touch the door and the door feels hot, that means there's a fire on the other side. So don't open your door, right? That's what that's telling you. So convection would be the heat transferred through a fluid. And when we think of a fluid, I know the first thing I thought of was a liquid, right? But a fluid actually means a gas or a liquid. And so you can experience this in your house if you have the heater on. You can put your hands up. I'm sure it's, maybe you're standing in the living room, put your hands up and you can feel this heat above you. Okay. So heat's always going to rise. And so literally there's like, hot air, up in your ceiling. So if you have really tall ceilings, like my boys, they have a really tall ceiling in their bedroom. So it's super hard for us to get the room to be warm because the current, right, that hot air is actually going to be floating up there instead of coming down where I need it. And then the last one would be radiation. So this is just the transfer of energy through an empty space. And so looking at the picture here, you can kind of see those examples, right, of convection. If you've ever, looked at a fire, you can literally see like waves, you can see that hot air that's actually moving up. Conduction, you could be touching something that's going to be transferring that heat. And then radiation, if you're off to the side, but not feeling the waves, like the heat, the gas coming out, then you're feeling it through radiation. So that could be also, if you've ever had a light bulb and you put your hand close to the light bulb, you're feeling the heat through radiation, because there's not like a flow of like gas, you know, warm gas that's coming out to you. All right, and so on your note-taking guide, there should be, all right, so we got the picture there. So if you just wanna, in your own words, kind of explain what conduction, convection, and radiation are. And then there is a quick little video. So as you're explaining, right?
This water
This
boiling,
will kind of give you some ideas.
the heat of the fire, and cooking on the skillet are all examples of heat transfer. In simple terms, heat is the transfer of energy from objects of different temperatures. As objects warm up or cool down, their kinetic energy changes. Kinetic energy is the energy of motion. Temperature is a measure of the average kinetic energy of the particles in an object. As temperature increases, the energy of motion increases. As the water warms up and the temperature increases, you can see an increase in the movement. Heat can be transferred in at least 3 ways: conduction, convection, and radiation. Conduction is a process in which the transfer of heat takes place between objects by direct contact. It is most often associated with solids. The key to conduction is direct contact. The heat of the pan is transferred to the mini pizzas. The energy of the frying pan is transferred to the eggs. Notice that they are in direct contact. Convection is heat transferred by the movement of a fluid such as air or water when the heated fluid is caused to move away from the source of heat, carrying the energy with it. It occurs due to density. Lava lamps are examples of convection. As the liquid is heated, it rises and falls as it heats and cools. As the paper burns, the air is heated up and begins to rise. The burning paper is swept up in the convection current, cools, and falls back down. These beans are another example of convection. As the beans warm up, they rise and then cool and fall back down, and repeat this over and over again. Radiation heat is transmitted without any physical contact between objects. Watch how the temperature of the lamp is transferred to the thermometer without touching it. These alligators and lizards use radiation from the sun to warm their bodies. If you'd like to know more about heat transfer and conduction, convection, and radiation, this playlist will help. And as always, thanks for watching, and Moo Moo Math.
Okay, so with heat, and when we think of the states of matter, heat can cause states of matter to change as well. So I did put a phase change graph on your paper there. And so melting is basically just the point at which we have a solid turning into a liquid. What's it called? Boiling is going to be where we have a liquid turning into a gas. And so these are the phase changes that can happen. With the phase change graph, this just kind of shows you that temperature can increase, but once I start seeing 2 phases of matter, so for example, here at the melting point where I see solid and liquid happening, the temperature is not going to change. So the temperature will stay the same, 0 degrees Celsius, until all of my solid is gone. Then it'll go ahead and temperature will start rising. Okay, and so I'm just thinking of water here, right? So water is going to freeze at 0. And it's gonna turn into a gas at 100 degrees Celsius. So when I reach 100 degrees Celsius, it's gonna stay at that temperature as long as I have a liquid and a gas. So I know, like, for example, I had students that would say, I'm gonna make it hotter by heating it up even higher. But once the water is boiling, you can't change the temperature of it. It's gonna stay 100 degrees Celsius, okay? And so the terms, right, for when we have those phase changes happening, melting is going from a solid to a liquid, boiling is going from a liquid to a gas, evaporation is going from a liquid to a gas, but with no added heat, right? So if I just leave a pot of water out, the water will evaporate on their own and I don't have to add heat to it. And then condensation will be when a gas turns into a liquid. I just noticed missing liquid there. So that, for example, if you have a glass on a hot summer day, right, you'll start to see water forming on the outside, and it's literally the water in the air that's turning into a liquid on your glass. Sorry for my child. Okay, so this video just kind of talks about phase changes, but I'm going to go ahead and skip that one so you can take a look at that one later. Okay, so next up we have electricity. And so with electricity, it's basically just electrons moving from one atom to another. And electricity could start from a battery, right? But we can get electricity from other places, such as solar energy or, electricity in the wall. But when we think of electricity, the flow of electricity is basically just called a current. And in order for us to have a current running, remember that we do have to have a circuit. So a circuit which has to run in a circle. That's what I always think of, circuit, circle. So if you look in the first picture here, the reason that the light bulb can turn on is because the switch is closed. So literally we have a circle, right, that's running. In order for the electricity to leave and come back to the battery. If I have the switch open, then the electricity doesn't have a circle, and so the light bulb will not turn on. Okay, and so that's why we got to think of a circle. So if I have a battery and a light bulb and there's nothing coming back to the battery, then I can't have a circuit because there's not a circle that's being created. Okay. All right, and then this one just kind of talks about, I want to say it's electricity, but dealing with also creating a current and a magnet. So with electricity, if I actually wrap an electric wire around something in a spiral, I can turn something into a magnet. Okay, so that's kind of how those two are related. Remember I mentioned that earlier. So with light energy, we want to remember the electromagnetic spectrum. And so the electromagnetic spectrum is basically just showing us waves, and depending on their frequency and wavelength, that's going to give us the different types of waves that we use every day. So for example, X-rays are a type of a part of the electromagnetic spectrum. We can't see them or anything, right? But they help us to analyze things. And then visible light is a really small portion of the electromagnetic spectrum. So that's all we can see. But there is like ultraviolet light, UV lights. Some insects can see using UV light. So they see things differently than we do. And then we, of course, use microwaves. We use radios, right? Our cell phones, all of them are using waves on a different part of the electromagnetic spectrum. And so when it comes to waves, right, there's different types of waves. So with these waves, I always think of like things I can see, right? When I'm thinking of the electromagnetic spectrum, I'm dealing with like vision, but we could also have waves that are dealing with sound, okay? So waves that we hear are gonna be moving through the air. So in the air, there's it's causing the particles to vibrate, and that's how we're able to hear things. So for example, in space, because there is no air, right? If something were to happen, I wouldn't be able to hear it because there's nothing for the sound waves to travel in. Okay, so this one just kind of clarifies the parts of the waves and all that.
What if you could only see one color? Imagine, for instance, that you could only see things that were red, and that everything else was completely invisible to you. As it turns out, that's how you live your life all the time, because your eyes can only see a minuscule part of the full spectrum of light. Different kinds of light are all around you every day, but are invisible to the human eye. From the radio waves that carry your favorite songs, to the X-rays doctors use to see inside of you, to the microwaves that heat up your food. In order to understand how these can all be light, we'll need to know a thing or two about what light is. Light is electromagnetic radiation that acts like both a wave and a particle. Light waves are kind of like waves on the ocean. There are big waves and small waves, waves that crash on the shore one right after the other, and waves that only roll in every so often. The size of a wave is called its wavelength, and how often it comes by is called its frequency. Imagine being a boat in that ocean, bobbing up and down as the waves go by. If the waves that day have long wavelengths, they'll make you bob only so often, or at a low frequency. If the waves instead have short wavelengths, they'll be close together and you'll bob up and down much more often, at a high frequency. Different kinds of light are all waves, they just have different wavelengths and frequencies. If you know the wavelength or frequency of a wave of light, you can also figure out its energy. Long wavelengths have low energies, while short wavelengths have high energies. It's easy to remember if you think about being in that boat. If you were out sailing on a day with short, choppy waves, you'd probably be pretty high energy yourself, running around to keep things from falling over. But on a long wavelength sea, you'd be rolling along, relaxed, low energy. The energy of light tells us how it will interact with matter, for example, the cells of our eyes. When we see, it's because the energy of light stimulates a receptor in our eye called the retina. Our retina are only sensitive to light with a very small range in energy, and so we call that range of light visible light. Inside our retina are special receptors called rods and cones. The rods measure brightness, so we know how much light there is. The cones are in charge of what color of light we see, because different cones are sensitive to different energies of light. Some cones are more excited by light that is long wavelength and low energy, and other cones are more excited by short wavelength, high energy light. When light hits our eye, the relative amount of energy each cone measures signals our brain to perceive colors. The rainbow we perceive is actually visible light in order of its energy. At one side of the rainbow is low energy light, we see as red, and at the other side is high energy light, we see as blue. If light shines on us that has an energy our retina can't measure, we won't be able to see it. Light that is too short wavelength or high energy gets absorbed by the eye's surface before it can even get to the retina, and light that is too long wavelength doesn't have enough energy to stimulate our retina at all. The only thing that makes one kind of light different from another is its wavelength. Radio waves have long wavelengths, while X-rays have short wavelengths, and visible light, the kind you can actually see, is somewhere in between. Even though our eyes can't detect light outside of the visible range, we can build special detectors that are stimulated by these other wavelengths of light, kind of like digital eyes. With these devices, we can measure the light that is there, even though we can't see it ourselves. So take a step back and think about all of this for a moment. Even though they seem different, the warmth you feel from a crackling fire is the same as the sun shining on you on a beautiful day. The same as ultraviolet light you put on sunscreen to protect yourself from, the same thing as your TV, your radio, and your microwave. Now those examples are all things here on Earth, things you experience in your everyday life. But here's something even more amazing. Our universe gives off the full spectrum of light too. When you think of the night sky, you probably think of being able to see the stars shining with your own eyes. But that's just visible light, which you now know is only a tiny part of the full spectrum. If we had to draw the universe and could only use visible light, it'd be like having only one crayon. Pretty sad. To see the universe in its full spectrum, we need to have the right eyes, and that means using special telescopes that can help us see beyond visible light. You've probably heard of the Hubble Space Telescope and seen its beautiful pictures taken in visible and ultraviolet light. But you might not know that there are almost 20 space telescopes in orbit, missions that can each see part of the full spectrum of light. With telescopes acting as our virtual eyes, both in space and here on Earth, we can see some amazing things. And the coolest thing of all? No matter the wavelength or energy, the light that we see out in the distant universe is the same thing as the light that we can experience and study here on Earth. So since we know the physics of how X-ray, ultraviolet light, or microwaves work here, We can study the light of a distant star or galaxy and know what kinds of things are happening there too. So as you go about your daily life, think beyond what your eyes can and can't see. Knowing just a little bit about the natural world can help you perceive the full spectrum around you all the time.
Okay, so there's a whole bunch of different waves, right? But waves are going to be traveling in some sort of medium. And so when we think of waves hitting a different density of something, then it's going to cause the waves to bend. So refraction is that bending of light that can happen. And you all experience this if you've been in a swimming pool, right? Your feet don't quite look the same, or they look like they're at a different distance from you. So that's just that bending of the light. As it goes into a different medium, it's going to slow down, and that's why it bends. And then when we think of lenses, a way that we can bend the light for our advantage would be using concave or convex lenses. And that's how we can get glasses or microscopes or even telescopes, so that we're able to see things, you know, closer or further away. And all we're doing is just causing that light to bend. Okay. And then this one just kind of talks about the waves and how they bend. So, and I'm going to go ahead and skip this one so we can move on, but you can take a look at this one later. So there are different ways that waves can bend, such as reflection, right? We see a mirror that's just bouncing back. Refraction is bending because they're going into a different density of medium. Reflection, refraction, and diffraction would be when the waves are going to be like breaking off. So into like your rainbow, like if I have a prism and the light goes into the prism, it's going to bend due to diffraction, and we can see the rainbow of colors. So sound is also a type of wave, but with sound, it's going to be a different type of wave in that I think of it as like a slinky. That's kind of how sound waves move. And sound waves are going to be moving through the air. So like I said, if you're in a vacuum, if you're in something that has no air particles, then there's no way that sound can travel, okay? Because it has to be moving through something. And so if I think of a slinky, if you look at this picture, think of a slinky, and that's kind of how the waves are moving. So kind of like, you know, and that's how we're able to hear things. So longitudinal waves are going to be like moving parallel to the direction the wave moves, and transverse waves move perpendicular. So we've got our longitudinal and our transverse waves here, and that's the difference between light and sound waves. And then our very last thing we have here is with, again, kind of talking about this energy of conservation of energy, and understanding how that energy can be transferred from one form to another. Also thinking about that law of conservation of mass. So mass will be conserved. And then there are different types of energy that, you know, we should be teaching to our students, such as natural, coal, oil, solar, wind energy, right? All of those. And they're basically just being transferred from one form to another when we use it. Okay, and then these will be our last questions.